Okay, so we're leaving that base 10, base 12 comparison behind. We're going to return to the geometry that we're exploring right now. You can see I've got a very colorful example of the pattern so far. And you can see that I've now drawn circles around the pairs of circles. So larger circles around the smaller circles. So this larger circle is defined by that section of dodecagon. So the diameter of these larger circles is 1.8 root 2, again, defined by the length of the dodecagon, a section of the perimeter of the dodecagon. And what that gives us is an actual unit. This is what it looks like here just by itself. And this particular geometric pattern is actually anchored on the circle that is defined by this 3.2 radius length. So that's the main length. And you can see here I've colored it in. So what we do next, our next step is to take the points that are defined by these smaller circles where they intersect the polygon that we created and connect them on either side of the center point. So we connect them on either side. Here I've colored them in just to show us that they have a thickness. And again, that thickness is 0.06 root 2. That's the distance between the circumference of these two black circles. And then again, the distance on the other side between the edge of the black circle and the white circle is 0.03 root 2. And so we know that when we can also, when we know the process that we just went through. So what I'm also doing here, you can see here, I've turned this basically, I've turned this sideways like that. So again, we're on a 45-degree line, and those points are defined by specific lattice points. We can draw two more circles and give us this line here through the center, or through on either side of that very specific 3.2 radius circle. So again, that's the main radius length that we're using. If I'm referring now to the diagram for 360 degrees, there's 30 rings. As we create 29 more rings that look just like this, the growth pattern of each of those rings, this ring has 12 of these circles in it. The next ring has 24, then 36, then 48. There's 30 rings in total. And on the 30th ring, we're able to use all the points that have been generated to create 360 points on the circumference of that final ring. So that would be the completion of the diagram for 360 degrees. But we can keep going with that, with ring after ring after ring. Again, I'm going to say it for millions and billions and trillions of rings. Once this pattern has been established, now we have the ratio between that length of 3.2 root 2 and the perimeter of the dodecagon, which is forming the structure. Basically, they're polygons, but we could think of that as like a framework or scaffolding, even if you want to, for the positioning of the points which define the circle. So we can keep the idea of dimensionless points on the circumference of a circle, but now we're able to create a space between them so that they're equidistant all the way around, equidistant from each other and from the center point. And in this way, we're creating sort of discrete lengths, and they're built in units of 0.5 root 2. And that 0.5 root 2 is a combination of 0.49 root 2 and 0.03 root 2. So we're combining the sections of the solid line and with a little bit of space between them. So this is essentially the journey, if you want to look at it this way, between the solid line of the diameter of a circle and its circumference, which is an irrational number, the irrational value of pi. So we see that an irrational number now does have empty space within it. That's what makes it irrational. Our current model of an irrational number is still a solid line with an empty space at the very end. And then we sort of add digits to the end, or little pieces of solid line to the end of that irrational number, but we never are able to close that gap. But we go until infinity. When the limit reaches infinity, we say, okay, we don't have to deal with that empty space anymore. So that's our current model, and it's something of a paradox. Without that empty space, the number wouldn't be irrational, but we don't want to admit that the empty space is there. So here we completely change that model, and we're integrating this empty space or this gap throughout the line. And we can see that we need to do this in base 12 because the ratio between the solid sections of the solid of the line, the diameter, and the space between them is a base 12 ratio of 0.49 for the radius of this circle, and then that 0.03 gap that's on either side. And we need this one unit that has the two. It's the relationship between the two circles of 0.06 root 2, half a length of 0.1 root 2, that's where all this, the balance and the precise relationship becomes evident. We can see it. It's visible in this geometric pattern. All right, so I do want everyone to know that I have written a book explaining all this, plus the process of creating the diagram for 360 degrees. This book is called Understanding Base 12 Math, How to Draw the Perfect Circle Using Dozenal Geometry. It's available through Amazon. And this book contains all of the information that I've already given you. And then it goes into the steps that we need to take to continue from this geometric structure and then build the diagram for 360 degrees. So it does involve drawing a lot of lines through the center, connecting these circles to those circles and building the diagram, filling in the gaps as it opens up across the different things. This is sort of what it looks like in there. And then we go over here. So it's a lot of geometrical patterns, and it was quite difficult to draw because this is one of the challenges, creating those grid patterns in base 12 and then lining up the points and everything. Our current geometric technology when it comes to illustrating geometric patterns is all in base 10. So it is a bit of a trick converting to base 12 and then showing what this looks like. That's why you're getting this presentation done on graph paper and a chalkboard. But that aside, you can see the logic of the geometry. I think I've been able to show you clearly that the structure is a valid geometric structure and is cohesive and balanced within itself, has integrity, has geometric integrity. So now what I want to do is the equation that is sort of lurking or very evident within this geometry is the actual division of the diameter of the dodecagon into its perimeter, which is becoming the circumference of the circle. Again, a scaffolding for those points. I know we say that a circle is not a polygon, and this isn't really a polygon because we have these separate circles with space around them. When we plot those and remove the perimeter of the polygon, we have a circle with spaces around each point that defines its circumference. So I'm going to go with the definition that we are building a circle, how to build the perfect circle using Dozenal geometry. And what we're going to do now is the equation. We're going to basically divide the diameter of this pattern into the perimeter, and we're going to look at the result of that equation. All right, that's the end of part 5. You can now proceed to the last video in the series, part 6.